Every single software project, it starts with this beautiful dream, right? Clean, elegant, super efficient code. But how often does that dream slowly turn into a nightmare? The code gets tangled, making a simple change feels terrifying, and that beautiful vision gets lost in this sea of complexity. The real question isn't just how this happens, but
Why? Why do good applications go bad? It's a problem that keeps developers up at night. This slow decay from beautiful order into just chaos. And you know what? This specific kind of chaos, it has a name. So let me introduce you to the villain of our story, the big ball of mud. And listen, this isn't just messy code, it's the total absence of architecture. It's what happens when structure just erodes away, information is shared everywhere with no rhyme or reason, and any sense of order is completely lost. It's the software nightmare every architect is desperately trying to escape.
And look, this isn't just some scary story we tell. It's a very real-world problem. This image right here, it's a visualization of an actual project's code base. Every single dot is a class, and every line is a connection between them. And the bolder the line, the stronger the dependency. It's a tangled web where making even one tiny change is absolutely terrifying because you have no idea what kind of side effects are going to ripple through the whole system.
Okay, so how do we fight back against this chaos? Well, we start by actually understanding the tools we have. And the two most fundamental ones are architecture styles and architecture patterns. Nailing the difference between these two is really the first step toward building systems that are actually built to last.
Now, people mix these two up all the time, but the difference is actually pretty simple, and it's powerful. An architecture style, that's the big picture. It's the overarching structure of your entire system. Think of it like the blueprint for the whole house. An architecture pattern, on the other hand, that's a much lower-level design that solves a very specific problem inside that house, like, say, the best way to design the plumbing to handle high water pressure.
in modern software, that very first, most fundamental architectural choice you make, it often comes down to this one single fork in the road. Are you building a single, unified system, or are you building a collection of interconnected services?
A monolithic architecture is a single deployment unit. Simple as that. All the code for the entire application is in one place. It's self-contained. A distributed architecture, on the other hand, that's made up of multiple deployment units. We call them services, and they all have to communicate with each other over a network using remote protocols.
So why bother going distributed? Well, the promise is huge. Incredible performance, massive scalability, high availability. It sounds amazing, but all that power, it's not free. It comes with a really complex set of trade-offs and a whole bunch of hidden dangers that can trap even the most experienced architects out there. And this is where we get to the absolute heart of the matter. If you choose to go down that distributed path, you absolutely must understand the fallacies of distributed computing. These are the assumptions that seem totally true on the surface, but in practice they are dangerously, dangerously false.
There are 8 of them. They were first identified by engineers at Sun Microsystems way back in 1994, believe it or not, and they are more relevant today than they have ever been. Believing in even one of these can lead your entire project straight to disaster. So let's break down the most critical ones.
All right, fallacy number 1. This is the first and probably the most common mistake, believing that the network will always just work.
Here's the hard reality. Networks are fundamentally unreliable. Connections drop, routers fail, packets get lost. It happens. In a distributed system, if service A can't reach a perfectly healthy service B just because of a network hiccup, the whole operation can fail. This is precisely why we need defensive tools like timeouts and circuit breakers baked into our designs. The second fallacy is the assumption that communication between all your different services is instantaneous.
Let's really put this in perspective. A local function call inside a monolith, that's measured in nanoseconds. A remote call over the network, that's measured in milliseconds. That is literally a million-fold difference. So if you chain just 10 of those service calls together, and each one has 100 milliseconds of latency, you've just added a full second to your response time. It forces you to ask the question, do you actually know your average network latency in production? Because you absolutely need to.
Next up is the dangerous belief that you have all the network bandwidth you could ever possibly need. Let's look at a classic example. Let's say a wishlist service needs to get a customer's name from a customer profile service. The name itself is tiny, maybe 200 bytes. But the profile service, instead of just sending the name, sends back the entire customer object, all 500 kilobytes of it. This is a classic anti-pattern called stamp coupling. Now multiply that mistake by 2,000 requests per second. All of a sudden, you're trying to push 1 gigabit of mostly useless data across your network every single second.
And the list just keeps going. Architects often wrongly assume the network is secure, or that the network topology never changes, or they think there's only one administrator to deal with, or that making remote calls doesn't have a real monetary cost in terms of infrastructure. Every single one of these is a trap waiting to be sprung.
And the final fallacy, this one is maybe the one that ties them all together. The dangerous assumption that the network is just this one single uniform thing.
The truth is, most corporate networks are a total mix of hardware from different vendors. Cisco, Juniper, and a bunch of others. And they don't always play nicely together. This can lead to dropped packets, which in turn makes the network less reliable, which increases latency and eats up bandwidth. You see? It creates this frustrating feedback loop that just makes all the other fallacies even worse.
So after all that doom and gloom, you might be thinking, is distributed architecture just a bad idea? And the answer is absolutely not. The point here isn't to declare a winner. The whole goal of a good architect is to understand that every single decision you make is a trade-off. There is no single best choice.
When you line them up side by side like this, the trade-offs become really obvious. Do you need massive scalability? Distributed is going to be the way to go. But what if you need ironclad data consistency? We're talking simple all-or-nothing bank transactions. Well, a monolith has the clear advantage there. Distributed systems often have to rely on something called eventual consistency, where data takes time to sync up, and trust me, that is a much harder problem to manage. And of course, deploying a single monolith is just worlds simpler than trying to orchestrate hundreds of separate services.
So ultimately, there is no magic bullet here. Escaping that big ball of mud isn't about finding the one best architecture. It's about consciously and deliberately choosing the right set of compromises for your specific problem. So the real question is for you, knowing the hidden dangers, but also the powerful benefits, which trade-offs are you willing to make? That's the decision that separates good architects from great ones.